Alright guys, welcome to the flipped classroom. We are going to be studying our exponential and logarithmic functions, and we get to start with exponential and logistic today in 3.1 and 3.2. So the whole chapter kind of bases on a lot of the exponential and the logarithmic stuff. Alright, so let's move forward. Let's kind of get into this. Let's kind of see how this is going to work. So first of all, we're going to start with exponential functions. What are they? What do they look like? That sort of idea. And all exponential functions look like the form a times b to the x power. Notice that the x is in the exponent. That's the key piece. A and b are both real numbers. A can't be 0 because that would be a boring function. And same thing with b not equal to 1. Both of those would just be flat horizontal lines. Not very fun at all. A is what we call our initial value, and it's kind of our starting point in real life sort of ideas. It's where time is 0, or the exponent there is 0. If you think about that, that makes sense, right? If b to the 0 power, that's 1, times a is just a, so therefore a is just our starting point. B is called the base of our exponent, or our exponential function. B is always called our base. It's just the base right there underneath the exponent itself. And like I mentioned, the x has to be in the exponent in order to have an exponential function. All right, and you might read this here in front of me. There are two different types of exponential functions, or two main types, and the first one is an exponential growth, and that's just if b is bigger than 1, then it's a growth, because you are basically multiplying by the same number a whole bunch of times, and it's going to be a bigger number, so it's going to be growing exponentially. And then likewise, it's an exponential decay if b is less than 1 and b is bigger than 0. So we're talking about our fractions here, not our negatives. We don't put b as negative anywhere. So what I want to do here is I want to just look at a couple basic functions. And these couple basic functions, f and g, are defined here in this table. And what we want to do is we just want to figure out what the functions could be. What could be the equations for the functions? So there's a couple things we can do here, and they're pretty straightforward. These two are pretty straightforward. These are kind of like our easy examples here. Give me just a second. Switch things over here. All right. So here's our example that we just had written down. For f of x and for g of x both, because of the way we have this example set up, is, well, I can kind of look at this and go, hey, I know stuff about my initial value, because my initial value is when x is 0, and x is 0 right here in the middle of the table. Well, if x is 0, this number 4 is my initial value, which means in all functions here we have a times b to the x power. Well, if a is 4, I can just use that 4 to help me out. Well, just like with all other things, we can just use a point that we have from this line now. Even though I've got 5 different points, it doesn't matter which one I use. And I can just say, hey, let's just use the easy one, 1/12. So if I plug in a 1, I should get out a 12. I divide both sides by 4. I get 3 is equal to b to the first power, which is just b, which means that's all I have. That's all I need. F of x is my function 4 times 3 to the x power. Now what you need to be very, very careful about, what you need to pay attention to, is the idea that this does not equal 12 to the x. No, no, no. Don't ever do that. Bad. Okay. So that's kind of the algebraic way to do this. We can kind of do it a little bit analytically, I guess, if you want to use that word, a little bit more intuitive. G of x is going to be the same idea, a times b to the x power. And in this particular case, we're not going to do a whole bunch of plugging in. We're just going to kind of think about what's going on with this function. I know my initial value is 8. So I'm going to use that 8, but I'm not going to plug in any points. I'm going to say, hey, what's going on as I go from the left to the right of this table? Well, I notice this is dividing by 4. And if you're kind of paying attention here, this is not a dividing function. It's actually a multiplication function, or repeated multiplication. And so what I want to know is dividing by 4 is the same thing as multiplying by 1/4. So that's what I'm going to write in here. I'm not going to use the 4. I'm going to use what we're multiplying by each time and bring it to the x power. And notice we didn't really have to do any plugging in to get that particular answer. We'll look at an example a little bit later that's going to have some little bit harder stuff to do, but not too bad for us. Okay, so that's kind of the basic ones. We'll get some better ones as we get going through our textbook itself. All right, so we're going to move on to your favorite, graphing. As with all new functions, even though it's technically not new for you guys, the exponential functions have graphs, just as all functions do. And we want to figure out what the graphs look like. So characteristics here are the initial value is our y-intercept, and that should be pretty intuitive to you. If we plug in 0, we get out the initial value, and therefore that's our y-intercept. Exponential growth is always increasing, so from left to right, it's an increasing function. And likewise for exponential decay, it's an always decreasing function. There's no symmetry on these graphs, so there's no even or odd on any of them. The domain is all real numbers, and the range is y is always bigger than 0, and this is always for the parent function. And parent function is kind of a loose term here because parent function is all dependent on b, the base. And we're going to look at one or two here in just a couple minutes, or a minute or so. The horizontal asymptote is y equals 0. You can never find an exponent to use that will ever get you out a 0 value. So we have a horizontal asymptote of 0. And again, it's for the parent function because we haven't shifted it up or down yet at all. We'll look at that in a moment. Like I said, the transformations are all the same as before. So when you go to the inside of the function, when you change the exponent, that's going to be moving left and right. It's going to change the x values. When you change the outside of the function, that's going to be changing our y's. You might want to read up on that from our last chapter. So we're going to look at a couple examples here. And we're going to look at our two basic functions here. We kind of like looking at y equals 2 to the x. This is our very first basic one. And if you want to think about plugging in a table, go for it. But for the most part, we're just going to find the points as we go. And you'll start noticing exponential functions are going to grow really quick. That's why we call it growing exponentially. So I can really only fit this much on my graph. And I'm going to go up 1, 2, 3, 4. And we're just going to go from there. We plug in their numbers here. If we plug in 0, well, 2 to the 0 power is 1, just here. Plug in x equals 1, I get a 2, 2 to the first power. If I plug in a 2 to the 2 to the second power is 4. And you notice if we keep going, it's going to get really steep really quick. If 2 to the third power is 8, and then 16, 32, going and going. Going in the opposite direction, you got to remember your negative exponent rules. You have to remember that 2 to the negative 1 is equal to 1 over 2. And 2 to the negative 2 is equal to 1 over 2 to the second power. So we're going to come back here. We're going to go back to a half and then a fourth. Then you're going to connect the dots here. And you'll notice here as you kind of sketch it in, there is no symmetry. It's not even because it's not the same on both sides of the y-axis. And it's not odd because you can't rotate the function around the origin. It's just, it is what it is. Never even, never odd. So that's my function, y equals 2 to the x. That's kind of a cruddy graph, but you know it's just a sketch. So this is 2 to the x power. And what we kind of want to do is, that's an exponential growth. You notice going from left to right, it's increasing. So it's an increasing function. It's growing as we go in the positive direction. What I want to look at now is kind of our basic exponential decay function, and it's 1/2 to the x. And 1/2 to the x we actually will be looking at a bit later when we start looking at things like half-life. But those are kind of fun examples, fun real-world examples. And you know I mean it when I say fun. All right, so same idea. Let's just go ahead and plot this. This won't take us too long because it's pretty straightforward. We're going to use the same values, just kind of compare. We're going to compare the two functions, basically. And you can just kind of follow along. Plugging in 0, I get 1. Plugging in 1, I get a half. Plug in 2, I get a fourth. And same kind of thing as before with the negative exponents. You have to remember negative exponents mean reciprocals. So 1/2 to the negative 1 is 2, and 1/2 to the negative 2 is 4. And same idea, you're just going to connect the dots in a decreasing manner like so. And there you go. What I kind of want to do now, though, is just look at one or two transformations. So we're going to move back up to the 2 to the x power. And in red next to it, I'm going to shift this function. Let's go 2 units to the right. Well, 2 units to the right is going to change my x values. And you have to remember the opposite. So 2 units to the right is going to be x. Well, to the right is plus, so I actually have to go minus 2. So that's going to move me 2 units to the right. Well, we're all pretty good at this now, so we're just going to move things 2 units to the right, or translate 2 units to the right. Got to extend my x-axis a little bit here. And in red, I'm just going to graph this 2 units to the right. So this point here, this coordinate at 0, 1, has to move 2 units to the right. And likewise for all of them. At x equals 1, it has to go to x equals 3. X equals 2, it has to go to x equals 4. And it's pretty straightforward. Kind of moving things just 2 units to the right. And there you go. That's your 2 to the x minus 2. Then why don't we just go ahead and, hopefully the blue shows up here. Let's just look at it going 2 units. Let's go 1 unit down. We go 1 unit down. That's going to be something to the outside, and this is exactly as you think. So it's 2 to the x minus 1. Now I'm a little bit low on my graph here, but that's okay. Going down 1 unit. Going down 1 unit. This 4 goes down 1 unit. Half goes down 1 unit. Fourth goes down 1 unit. And then we'll just connect the dots here. And all these functions should look identical because all we're doing is moving stuff up, down, left, or right in these particular cases. They're exactly the same function. And you can do all sorts of things. You can say, hey, let's have, we're not going to graph this one, but just kind of think about it. Y equals 3 times 2 to the x power. That's a vertical stretch by a factor of 3, so we're just going to multiply all of our y values by 3. So this point here would go up to a 3. This point here would go all the way up to a 6, and I've already lost my graph. Okay, that's why we're not going to first graph this particular one. All right, so that's kind of the graphs. The graphs are pretty straightforward, I think, but I'll be here for help tomorrow, that sort of stuff. Okay, so one of the things that we do when we get into exponentials and logarithmics is we look at the natural exponential function. That just means we use the letter e, or actually rather the number e. Some of you guys might remember this from last year, the number e. You can find it on your calculator. Those of you guys with the TI-83 or the TI-84, it's always in the same spot for both calculators. And somebody's using the plot on mine. You look right down here at e to the x power. And this is a pretty cool number. It's kind of like pi. It never stops. It never repeats. And it's called a transcendental number. All that sort of fun stuff that us math nerds like to talk about. So if I want to figure out what e to the first power is, I'm just going to hit the blue key first, then e to the x. You'll see this on the screen here. To the first power, and you'll notice it comes out with this number. It really does look like it repeats, but it's only because your calculator can only see so many digits, or can only present so many digits. But it actually is a non-repeating decimal, and it's kind of cool that the only thing that your calculator can show is one of the only repeating spots on the entire number. It's kind of an interesting thing. So 2.718281828. See, all of you guys can memorize that much. Easy. Not that you ever need to, but who never needs to memorize pi either, right? So this is named after Leonard Euler. His name is Euler, not Euler. You're not allowed to say the word Euler. So Leonard Euler, he was one of the great mathematicians back in, you might see there, the 1700s, way back when. One of the things that we're going to be doing, as I said, is actually a lot of mathematics deals with the letter E, and we only deal with natural logarithms coming up and natural exponentials. And what we do is we sometimes rewrite all of our functions as the natural exponential function or natural logarithmic function. Why I've never quite figured that out, it's just it's a more common thing or a common base to use than the others. In the form a times e to the kx, k is any value, whatever makes e to the k equal to b. And if k is bigger than 0, then it's an exponential growth. And if k is less than 0, then it's an exponential decay. And like I mentioned, we're going to get to this a little bit later on how to change b into e to the k as we continue through the chapter. One of the other things we deal with is the logistic function. Sorry about that. The logistic function is kind of a real world example of where this stuff is going to get used. And it looks like this. This is the basic version here. It's c over 1 plus a times e to the negative kx. And the parent function for this particular graph is if a, c, and k all equals 1. And you can go graph this if you want. You can look in your textbook if you want. And you can kind of see what the parent function looks like. C is what we call our limit to growth. It's how big something can get. You guys some of you guys in biology might understand things like carrying capacity, that sort of idea. C is our limit to growth, how big something can get. And one of the things I want you to make note of in the textbook is the analysis, kind of like our mins, max, horizontal asymptotes, vertical asymptotes, increasing, decreasing, domain, range, all that sort of fun stuff. That's on page 284 of our textbook in the yellow box. This particular piece here, the note the in behavior, is kind of something we've kind of been skirting around lately, and that has to do with limit. And it just means, in this particular case, we're looking at the limit. The limit as x approaches infinity of f of x. Actually, in this, the left side there, the first one is negative infinity, is equal to 0. So as x goes towards negative infinity, the function itself goes towards 0, and that actually means there's a horizontal asymptote at y equals 0. And the one on the right there says the limit as x approaches infinity of f of x is equal to c. So that means as x gets really, really big, the function approaches c, and that kind of thinks about our carrying capacity in that sense. Well, like I said, we'll get more back into limits as we get going here. So there's a lot of real life situations that are modeled with the logistic function, and one of them is like bacteria. We have population growth of a city. Cities can only get so big, that sort of idea. Now I know this is kind of out of order here just a little bit, just kind of end up being that way. This is not a logistic function here that we're going to create the equation for. We're actually just going to create the equation for a basic exponential function. So this is kind of a real world thing here, and what this is year in population, as you see there, and the year 1990 and the population 782,284, and the second year being 2000 and 894,943. And what we want to figure out is an exponential function that models this data, and we want to figure out how long it will take to reach 1 million people. So looking at those two coordinates, what we're going to do is we're going to create just a very simple exponential function. And the exponential function being a times b to the x power. And this is one of those kind of, not really more challenging ones, but it just takes a little bit extra piece here to solve it. And what we're going to do is we're going to say, in a lot of these problems, we can just say, hey, that first point is going to indicate our initial value. So that's kind of nice for us, because if that's our initial value, we already know that for our function. Well, the same thing as before, all we have to do is, in order to find the b value, is plug in the other point, the other piece that we do know. And we don't want to use the number 2000 because that would indicate 2,000 years after this first piece. But since our initial is at 1990, we can just use the value of 10 for x to figure out what b is. So we're going to say, okay, we're going to get out a y of 894,943 equals 78, I wrote an 8, 2284, b to the 10th power. Well, we kind of know how to solve this. I think b to the 10th power is equal to 894,943 over 782,284. Well, if I said this was b squared equals this thing, you would square root. If it was b cubed, I would cube root. Well, if b to the 10th, I'm just going to 10th root. Now, I could get some decimal approximations here, but you know me, I don't like doing that at all. I'm just going to plug that into the calculator just as so. And if you don't know how to do that, go to your handy-dandy calculator. And under math, we have some good stuff. You'll notice here we actually have an X root, and if you have the newer operating system on the 84s or even the newer 83s, if you hit that, look what comes up. You can type in 10th root of, I need the fraction there. I'm just going to write it as a fraction. Division here, 894,943 divided by 782,284. Hit enter. Oh, look, there I go. There's my B value is 1.01. So B is equal to 1.01. And I'm just going to write that back into my function, into my equation. I'm going to say y equals 782,284 times 1.01 to the x power. And then that's not actually finished on my question, because the question says, hey, find the equation, but then also figure out when is that going to reach 1,000,000. Well, that's not too bad. I can just say, hey, when does it equal 1,000,000? We don't really have the skills yet. You might remember some of them from last year on how to solve this. So we're actually going to solve this a little bit easier way. We're going to solve this graphically. So you're just going to go in here on your graphing calculator, and you're going to type in both of those functions. You might be thinking, what two functions? Well, here's one of them. Here's y1, and here's y2. And we're going to figure out where they intersect. So real quick here, we're going to go, let's see if I can actually type in here, 1,000,000, 6 zeros, looks that way to me. And then 782284 times 1.01 to the x power. Now before I go graph, I know my y value has to be well over 1,000,000. And my x value might not take very long, but it'll take more than 10. Because of what was given already. We already know at 10 it was at 894,000. So I'm going to change my window. Don't worry about shade res, that doesn't make sense to us. We're going to go from 0, let's go from 0 to like 25 on the x direction. And I'm going to start at like 900,000. And I'm going to go up to let's go 1.1 million, because I don't really need anything else other than that. And I'm going to go by something quite large, just so I don't have a whole bunch of dashes on my graph. I'm going to graph. There's my 1,000,000. Where's my line for 1,000,000? Where's my line for the exponential? Oh, look, there it is. Oh, dang it, I missed. Well, that just means I got to change my x values. I need to change my x value to about 35 or so. Sadly, that means it has to regraph. Do a quick intersection under calc. So we got to go second calc, intersect, enter, get close to the intersection, hit enter again. Notice our intersection's at 24.68. So x equals 24.68 years. So that's about the year, what, 2014? 2014, somewhere in there. So this particular city has already crossed 1,000,000 in our current time. I think that's kind of wrapped us up. Oh, I lied. What we have here is a little piece for 3.2 that you're going to kind of need here, and it's just a basic equation. And this is the exponential population model. We can write an equation where population is changing for time at given rates. And population doesn't have to mean people or things. It could just mean weight. Like in this particular example, I have an initial mass of 15, which is p sub 0. I have a rate of 4.6%, so it's 0.046. And in this particular case, I know the thing says it needs to be in time or in years, time in years, but in this case I changed it to days just because we can do things in days, especially since I don't want to think about a year. It'd be out of 365 or something. So notice my exponent I changed to x over 2. So if I plugged in 2, I get one rotation or one iteration of the change in percent. Okay. In this particular case, we were decreasing, so I had to do subtraction here. Most of this is pretty intuitive, I believe, plugging things into this particular function, and that's our 3.2. And when you get to your calculator and looking at regression models, you can use the logistic model as well, the logistic regression. Here's our assignment. I know the video is a little bit long today, but I'm sorry. This is gonna kind of, like I mentioned in class, we're gonna kind of tweak this. We're gonna change it as we go, and hopefully this is one of the longest ones. So I hope to see you tomorrow, ready to go. I hope I made a little bit of sense to you today, and yeah, I think we'll do pretty good. So until tomorrow, see you guys. See you guys.